In this lesson, we're going to start with a gentle introduction to Fourier transforms. And this is gentle in two ways. First, we're going to start with one-dimensional signals instead of two-dimensional images. And second, we're going to use code to play around with Fourier transforms before getting into the mathematics of Fourier transforms. So what is a signal? A signal can be thought of as a stream of numbers or a sequence of values that vary as a function of time, like a person's heart rate or the stock market prices of a particular stock. Or more rigorously, a signal is a one-dimensional array where each index corresponds to a uniformly spaced time point. So here's a signal I created. It has a duration of 1 second. It is a sine function that has a frequency of 5 hertz. That's 1, 2, 3, 4, 5 bumps per second. And it has an amplitude of 2. From here to here, it's 2. And the way I created it is using this code. The frequency is 5. The amplitude is 2. I took a 1 second interval and I split it into 1,000 pieces, and I created 1,000 time points. And then the signal is created by taking a sine using the amplitude and frequency. And then I plotted it. So what you see that appears to be a continuous signal is actually composed of 1,000 discrete time points, and this is important when we talk about discrete Fourier transforms. So we have this signal, and now we can make a composite signal. This time we specify a frequency and amplitude for the first signal, that's 2 and 1, frequency and amplitude for the second signal. For the first signal, I picked a cosine function, for the second one a sine function, and then we just sum up the two signals and we plot them, and here it is. The first signal has a frequency of 2 and an amplitude of 1. The second one has a frequency of 4 and an amplitude of 3. And when we sum them, we come up with this composite signal. The idea of Fourier transform is that given a composite signal, we should be able to retrieve the original elementary sinusoidal signals that composed it. And again, before we get into the mathematics of Fourier transform, let's get some intuition for it. So again, the main idea that Fourier came up with that's really revolutionary is that any signal in nature, no matter how complex, can be represented as a weighted sum of sine and cosine functions of appropriate frequencies. And what the Fourier transform does is that it decomposes the complex signal into its frequency components. So again, here we have a signal that is composed of two other signals. And with the Fourier transform, it is projected from the time domain into the frequency domain, so that now we have the two elementary sinusoidal signals that composed it. And then we plot on the frequency spectrum these two different frequencies. The first function appears to have a frequency of 2, and the second one looks like it has a frequency of 3. So that's 2 and 3 on the x-axis, and the y-axis represents the relative magnitude of each signal. And here is an animation from Wikipedia. We start with a complex signal in red. It's composed of many elementary signals, and the Fourier transform says that it's a weighted sum of sines and cosines, and it projects it onto the frequency domain to discover all of those elementary signals, and then we plot the frequency spectrum. So let's get into this with some code. We're going to use SciPy's fast Fourier transform, and we'll talk about what fast means later. And for now, all we need to know about this function is that it returns an array of complex numbers that encode the magnitude and the frequencies in the original signal. The magnitude of the signal at each index in this array can be retrieved by simply taking the absolute value of that particular Fourier coefficient, and the frequency for each coefficient can be retrieved by using this SciPy function, which takes two arguments. It takes the length of the signal, n, which is really the number of samples in the signal. In our case, it was 1,000 samples. And the the sample spacing, in this case, our time step was 1,000 in the preceding code. So here's the code. We import the two functions we talked about from SciPy. And then we get our composite signal that we created before, which is this signal over here. And we submit it to the fast Fourier transform, and we end up with the transformed signal. And as we discussed before, at each index in this array of complex numbers, we can get the magnitude of the signal by just taking the absolute value, and we can determine the frequency by using this function, which takes the length of the signal, which is 1,000 samples, and the time step between the samples. And we plot that, and here's our frequency spectrum. As expected, we have two elementary signals. One has a frequency of 2, one has a frequency of 4, and the relative magnitude of the frequency 4 signal is 3 times that of frequency 2 signal. And that's consistent with what we started with. The first one has a frequency of 2, the second one has a frequency of 4, and the amplitude of this one is 3 times that of that one. There is a Colab notebook that accompanies this lesson, and it is linked in the slides, and I'll also link it in the description of this video. Feel free to create your own composite signal composed of 2 or 3 or 4 different elementary signals, and then apply the Fourier transform to see what type of frequency spectrum you end up with. Now let's talk about inverse Fourier transform. As the name implies, the inverse Fourier transform maps the signal back from the frequency domain to the original time domain. And the key idea is that the Fourier transform preserves all of the information in the original signal. So if we start with a signal S and take its Fourier, and then take the inverse Fourier of that, we end up back with the original signal exactly without any loss. And this is a really key idea. The whole impetus behind using the Fourier transform is that we first take the Fourier of the signal, then we do some interesting things in the Fourier space, in the frequency domain to that signal, and then we take the inverse Fourier of that to end up with our modified signal. So how do we take the inverse Fourier transform? Well, we're going to use SciPy's inverse fast Fourier transform. Again, we'll talk about what fast means later. And it's very simple. We have our transformed signal from the previous code, which is an array of complex numbers, and we take the inverse of that. And it turns out the IFFT function also returns an array of complex numbers, but unlike before, where we were interested in both the real and imaginary parts of the complex numbers to get our magnitude and frequencies, this time the imaginary part of the complex numbers is very small and we're not really interested in it, and we are only interested in the real component, which gives us a reconstructed signal in the time domain. So we have our reconstructed signal, and we can plot it. Here it is, and we can compare it to the original signal. They look identical. So far we've been dealing with a toy example. Our composite signal was not really very complex. In fact, if you look at it, you could tell that it's just made up probably of two other elementary signals. But what if we have a truly complex signal? So let's look at that. I took a sound recording of a guitar sound. I downloaded it from the internet, and I loaded it here. And it was like 10 or 15 seconds long, so I'm only interested in a 1 second duration of it for the purpose of this lesson. And I'm just plotting it. This is what the sound signal itself looks like in the original time domain. I have taken a 1 second duration of that signal, and this 1 second duration actually has 44,100 time samples, and that's just a property of the recording device that was used to record this sound. It sampled it at a rate of 44,000 hertz. So looking at this signal, it's not obvious at all that it can be decomposed into the sum of sine and cosine functions. So let's see if we can achieve that. So we will apply the Fourier transform to it. So this is our guitar sound signal. We take the fast Fourier transform of that. And just like before, we extract the frequencies and magnitudes from this array of complex numbers using this code, and then we plot it. And sure enough, we end up with a nice frequency spectrum. Here, I've actually only plotted the frequencies ranging from 0 to 5,000, which human hearing is more sensitive to. And you will see that even within this range, only a few of these frequencies have any significant magnitude, and this becomes important when we talk later about signal compression and image compression. So now we have this signal transformed into the frequency domain. Let's see if we can get it back to the original signal reconstructed in the time domain. So here it is, our transform signal. We take the inverse Fourier transform of that. We take the real component of that. This is our reconstructed signal, and we plot it. It sure looks like our original signal, and we can prove that by taking its root mean squared error. This is the original signal. This is the reconstructed signal. We subtract them to end up with the error. We square it, we mean it, we take the square root. So root mean squared error. And when we print it, the root mean square error is in the order of 10 to the negative 13. So it's essentially 0. So this process of going back and forth between the time domain and the frequency domain is lossless. This tiny loss is just due to floating point errors. And that's a really important concept. So in summary, we began with one-dimensional signals to describe Fourier transforms before we move on to two-dimensional images. The main idea of the Fourier transform is that any signal can be represented by a weighted sum of sine and cosine functions of appropriate frequencies, and that the Fourier transform maps a signal from the time domain to the frequency domain. The resulting frequency spectrum contains all of the information in the original signal, and that's super important. And because of this property, we can use the inverse Fourier transform to map the signal back from the frequency domain to the time domain and reconstruct our original signal. The output of Fourier transform is an array of complex numbers that happens to be the same length as the original signal array. Both the real and imaginary components of each complex coefficient in this array are important for getting our magnitude and frequencies. And then the output of an inverse Fourier transform also happens to be an array of complex numbers, but this time the imaginary component of each coefficient is small, and we are only really interested in the real component because after all we're dealing in the real world with a real signal that has no imaginary component. So next we're going to talk about the mathematics of Fourier transform before we get into the applications of Fourier transform and why this is all important.